Swayam Prabha. Digital India. Educated India.
We will consider comparison of stresses in simply supported and clamped plates under uniform pressure. These are the two typical plates. They are circular in shape, and then we have the end conditions like this in the case of simply supported, and we have the end conditions shown here for the case of clamped plate. The radius is A, height is P, or thickness of the plate is H. So, and pressure is P. So, we would like to now show you the stresses acting in the radial and tangential direction in the two cases. So, we will plot now, we will consider the stresses to be plotted in the vertical direction. Radial direction x is plotted in the horizontal direction. So, we will have sigma 1, sigma 2, and for the simply supported plate the variation is this is the variation of sigma 2, this is the variation of sigma 1, similarly for the case of clamped plate this is the ratio is this is the extreme outer radius. So, therefore, it is unity here. Similarly, if we consider this case, the variation sigma 2 is like this, sigma 1 is this. Again, this x by a is unity at the outer radius. The magnitude of the stresses, if we write for this case, the maximum stress which occurs at the center is 3 by 8 1 plus nu p a square by h square, and the value of stress sigma 1 is compressive 3 by 4 p a square by h square, and this magnitude of sigma 2 is minus 3 by 4 nu times p a square by h square. And the value of stress here, this value we will write it here. It is 3 by 8, 3 plus nu p a square by h square. And the stress sigma 1 is 0 and sigma 2 will have some value here. Now, note this, that the stress at the center in the clamp plate is much less. It is, if you forget about the value of nu which is less than 1, you have the stress in the case of simply supported plate almost 3 times that of the stress in the case of clamped plate. So, higher stresses are going to develop at the center of the simply supported plate. And if you remember, the deflection, maximum deflection is also going to be high or rather higher in the case of the simply supported plate. Now, let us try to understand why the stresses are going to be, in this case the stress here is going to be now positive. On the other hand, these stresses are going to be compressive in the case of clamped plate. So, this can be understood even from physics of the problem. So, for that, let us consider again the plate. Now, we will focus our attention on a portion of the plate, a strip which is oriented close to the center. Now, if you consider this to be a simply supported plate, this segment is going to deform like this. So, this is the direction of stress sigma 1 and this direction corresponds to sigma 2. Since the plate is bending like this, we would expect tensile stresses to develop all along, and that is what is here. Sigma 1 is all along tensile stress, and since at the edge of the simply supported beam the bending moment is 0. So, therefore, the bending moment in this direction m is 0 in this case, but little inside it will be positive, but it is going to have a direction like this. Similarly, here the direction like this, that is the direction of m1. Now, since the tensile stresses are developing at the bottom edge, compressive stresses are developing at the top fiber, or tensile stresses are developing at the bottom fiber and compressive stresses are developing at the top fiber. Because of the anticlastic curvature, this will try to bend like this, but we are trying to keep the plate all the time touched to the support. So, therefore, the support is now going to apply some moment which will be acting like this, which will try to undo that curvature. So, therefore, this is what is the moment which is going to come up at the outer edge on the plate, and this is what is going to be the direction of M2. And in our convention, this is positive moment, and hence this moment is going to produce now compressive stress. It will produce the tensile stress at the bottom and compressive stress at the top. So, therefore, you find that tensile stress is going to develop at the bottom fiber, and that is what we have found here, that it is positive stress. So, once again, because of the anticlastic curvature, this is going to bend like this, but it has got to be flat to be in touch with the support. Support is going to apply some moment which is going to be undoing this curvature, and that moment has got to be directed like this. And if this is the moment acting here, we must have tensile stresses developing at the bottom fiber and compressive stresses developing at the top fiber, and we are plotting the stresses here at the bottom fiber of the plate, and therefore, sigma 2 is positive as expected. Now, let us try to see the difference in the case of clamp plate, which I have already stressed in my last lecture. Let us again look into, so that you can see the comparison between the two. In this case, is portion at the center is going to deform like this. So, here again from the center we can show our direction sigma 1, and this is direction sigma 2. For this case, the moment that is acting at the edges, it is clamped, and therefore, there will be non-zero moment at the edges, and this moment is going to be like this. So, this is the direction of moment m1, and under the action of this moment m1, we are going to get tensile stresses at the top and compressive stresses at the bottom. So, therefore, tensile stresses in the direction sigma 1, we are going to get compressive stress at the bottom, and that is what is your sigma 1 stress is compressive here. Now, if this is the moment acting, the strip will try to have anticlastic curvature like this. So, it is going to be curving with the center of curvature at the top, and since this curvature cannot be permitted because it has got to be in contact with the support, this has got to be undone. The support will apply moment, which is going to be now in this direction m2, and this is negative, this is opposite compared to what we have seen here, and therefore, under the action of this moment, we are going to get now compressive stresses at the bottom, tensile stresses at the top, and therefore, we expect sigma 2 to be compressive, and that is what we have got here. So, this is how that the stresses are going to be different in the two cases. We can have plates of different geometry and also support conditions, and they are all going to be met in practice. So, we would like to consider some geometries for further elaboration on the procedure. So, let us now consider one case wherein the plate is with concentrated load at the center. So, this is the geometry that we will focus upon, that we have a cylindrical shell, and then we have the wall there, it can be a closure, and there is one boss, and on the boss some external load P is acting, and in this case the dimension here is A and the internal radius is B. So, we can consider, since this dimension is very large compared to this height of the plate or thickness of the plate, we can consider that the condition here is nothing but a clamped condition. Similarly, this dimension is so very large compared to the height or thickness of the plate here, and therefore, we can consider that this is also an edge with clamped conditions. Now, for this problem, therefore, when it is deforming, it is going to deform like this. Schematically, we will have the deformation looking like this. So, this P is now not 0 and small p, which is uniformly distributed pressure, that is 0. So, let us try to go over the derivation of deflection and also calculation of for the stresses in this case. As usual, we will consider a radial portion of the plate which is at a distance x. We consider that portion, and therefore, you can now consider that area. Since we are interested in finding out the shear force per unit length of the circumference on this circle, we will have 2 pi x into V, that must be equal to the total load. So, therefore, V equal to P by 2 pi x. And now, we will have phi the relationship that we have derived last time. There we substitute small p equal to 0, and hence we will get the expression for slope phi. It is nothing but p by 4 pi d into x ln x minus x by 2 plus C1 by 2x plus C2 by x. So, we have obtained this phi making use of the solution that we had derived in the last lecture. Therein we have simply knocked out the expression involving small p, and we are left with this expression for phi. Now, what are the boundary conditions in this case? So, let us look into the boundary conditions. Obviously, in this case, this is x is equal to a and this is x is equal to b. What we have is that slope here is 0, here also it is 0. So, we can write the boundary condition to be at x is equal to a and x is equal to b, phi is equal to 0. And now, if we put the value, we are getting now from this relationship C1 by 2a, C2 by a is equal to p by 4 pi d a ln a minus a by 2. So, let us say that is equation number 1. So, we have simply substituted x is equal to a, and then since phi is 0, we have taken this part on one side and the other part to the right. This should be plus. Similarly, we can write C1 by 2b, C2 by b is equal to p by 4 pi d b ln b minus b by 2, and let us consider this as equation number 2. So, we have two constants of integration C1 and C2, they can be resolved easily, and after solving these two equations we get the constants as follows. P by 2 pi d into a square ln a minus b square ln b divided by a square minus b square minus half, that is C1, similarly C2 is given by P A square B square by 4 pi d into ln b by a divided by a square minus b square. So, we can substitute the value of C1 and C2 back into the expression for phi. Finally, we get phi in the form minus p by 4 pi d x ln x minus x by 2 plus px 4 pi d into a square ln a minus b square ln b divided by a square minus b square minus half. So, that is parts involving C1, and C2 is P A square B square by 4 pi d x ln b by a square minus b square. So, we have got now phi, and now we can calculate the bending moment, which is necessary for calculation of stresses. So, if you calculate now bending moment is given by m1 is given by modulus of rigidity d into d phi dx plus nu into phi by x. So, once we do that, if we substitute the value, we get the following. So, it will give us ln x plus 1 minus half plus p by 4 pi d a square ln a minus b square ln b a square minus b square minus half. Then we have minus p a square b square 4 pi d x square ln b by a square minus b square plus nu times phi by x, that will give us minus 4 pi d ln x minus half plus p by 4 pi d into, it will be really this expression repeated here. So, I will not repeat, that will come, and then we will have another portion p a square b square by 4 pi d x square ln b by a square minus b square that is the whole expression. So, this is m1. Similarly, we can really have some simplification for this one. for this expression, and we can write it little in an eta form. So, if we write that in a simplified form, some cancellations are possible. So, we can write now m1 is equal to minus p by 4 pi p 1 plus nu ln x by 4 pi. So, that is the term which we get starting from this the term here, that 1 we can take out, and then p into 1 plus nu by 4 pi a square ln a minus b square ln b by a square minus b square minus p a square b square by 4 pi x square 1 minus nu ln b by a square minus b square. So, this is the expression for m1. Similarly, m2 will be given by d into phi by x plus nu times d phi dx, and if we substitute the value of phi and d phi dx, then after simplification you can get m2 this also looks very similar. So, we have the portion from phi by x, and then we have the following for d phi dx. Nu times d phi dx gives us nu into minus p by 4 pi d ln x plus half plus p by 4 pi d into, again we will have this expression coming here. So, we can avoid that same expression, and then minus p a square b square by 4 pi dx square ln b by a minus a square So, this is the expression for M2, and once you simplify this, this looks like the following: minus nu p by 4 pi minus p into 1 plus nu by 4 pi ln x plus p 1 plus nu by 4 pi into a square ln a minus b square ln b by a square minus b square minus p a square b square by 4 pi dx square into 1 minus nu ln b by a square minus b square. So, finally, if you calculate the stresses, if you want to calculate the stresses at the location r equal to a, you can evaluate the bending moments. So, substituting x is equal to a in the two expressions here and in this expression, you get the bending moments which are critical. So, we will get now m1 at x is equal to a, it is p by minus p by 4 pi minus p 1 plus nu by 4 pi ln a plus p into 1 plus nu by 4 pi b square ln b minus a square ln a minus a square by b square plus p b square 1 minus nu by 4 pi ln b by a, it is b square minus a square. This minus sign we are just trying to absorb, so therefore it is, so this should be also b square minus a square. This we have changed the position of the term, so therefore this should be b square minus a square. So this is b square minus a square. Similarly, m2 at x is equal to a is equal to nu p by 4 pi minus p 1 plus nu by 4 pi ln a plus p in 1 plus nu 4 pi, and in fact we have the same term here. So, this expression b square ln b minus a square ln a by b square minus a square plus p b square into 1 minus nu by 4 pi ln b by a by b square minus a square. So, you have the expression for the bending moment at the location x is equal to a given by these two expressions, and you can see that the bending moment is higher in the direction 1, because this is p by 4 pi and this is nu p by 4 pi, nu is less than 1, and therefore this m1 is more significant than m2. So, therefore, now we can calculate the stresses by using the formula, which is nothing but sigma 1 is given by 6 m1 by 8 square and sigma 2 will be 6 m2 by 8 square. So, look at the deformation of the plate again, that we are going to get now the bending moment acting like this. So, the bending moment is m1 is acting like this. At x is equal to a, it is going to act this way, and at x is equal to b, it is going to act like this. See, the shape of the plate is going to be like this, and therefore, this curvature can be generated only when the bending moment is like this. Similarly, this curvature can be generated only when the bending moment is acting in this direction. So, therefore, this is going to be m1 at x is equal to b. So, we are expecting stresses to be at the center, we are expecting tensile stress to come up here, compressive stress at the top fiber, and we are going to have exactly opposite tensile stresses at the top fiber and compressive stresses here at the bottom fiber. So, this gets changed. You can consider plates of various geometry. We will have also problems of this type. You can have a plate which is having a cutout at the center like this. It can be supported at the edges, it can be clamped at the edges, there can be distributed pressure over this portion. Let us say that the x is equal to A to B, there can be distributed loading, there can be concentrated loading acting at the inner edge, and many combinations are possible. So, all these problems can be very easily solved by following the procedure that we have given in the last lecture and in the lecture today. Many problems of this type have been solved. Finally, what you find is that the stress is going to be related to the distributed pressure P or concentrated load P, and it is possible to write these stresses in this form. So, for general problem you can write like this, that we are going to have problems involving P capital or pressure P. So, we will have problems involving various geometry and concentrated loading or distributed pressure. Now, it is in all the cases one thing will become clear. We have, of course, we have derived this sort of relationship in the last lecture. You will find that the maximum deflection is going to be of this form. There is a constant multiplied by P if it is distributed pressure, dimension of the plate A raised to the power 4 divided by E H cube. So, that is the type of form which you will always get, and of course, this K is going to absorb the constant related to the Poisson's ratio. Similarly, if it is the case of the concentrated load, then we will have another constant, and then it is going to look like this, P A square by H cube. And the stress, you can see the stress here is going to be proportional to H, inversely proportional to H square, and we can write in general form that sigma maximum is equal to some constant K P A square by H square, and it will have the dimension of the pressure. Similarly, if it is a concentrated loading, then it is going to look like this, P by H square, and this P has a dimension per unit length. So, with this sort of constants can be these are the expressions for W max and sigma max under the various conditions. We can the people have solved this type of problem and they have given the data in a tabular form. Now, it is not necessary to derive all these formula and calculate the maximum deflection or the maximum stress. This data can be directly taken from the tables and calculation can be done. So, we would like to look into those tables now. We will consider now the various geometry of the plate and supporting conditions. I have shown here 5 cases. You have a plate here which is having a circular cutout at the center. Let us say this is of radius equal to A and the outer radius is B. So, we will maintain that nomenclature. We have P load acting at the inner edge of the or at the edge of the cutout, and it is simply supported at the ends. You can have a situation like this, the support is along the circumference of the cutout and the pressure loading is acting. This is the second case. Third case is that you have the support at the center through the boss and the distributed loading is coming up like this, and here we have the plate clamped at the edges and the loading is acting at the center through the boss, and the boss outer radius is equal to A. And here it is very similar to that case, but we have the concentrated force here plus the pressure acting at the top. So, for various ratios of this radii B by A, you can calculate the constants, and we would like to give you those constants. What I am trying to give you here is that you can calculate sigma maximum for the case of distributed pressure taking the constant K or K for the concentrated loading. Similarly, if you want to calculate the deflection maximum, then you collect the K1 from this table corresponding to the geometry that you have. We have given the 5 cases which are shown here, and this B by A ratio. So, this should be B by A. So, this is B by A ratio, B is larger radius. So, B by A ratio we have given in the row here. In one case we have 1.25, another 1.50, there can be other values also. Now, for the case 1, what we have, when B by A is 1.25, then K is 1.10, K1 is 0.341, and if B by A is 1.50, then K is 1.26, K1 is 0.52. Similarly, for the case 2, you have the values of this constant for the two radii ratio, and similarly for the case 3, 4 and 5 the data are given. These are solved in the middle of the 20th century, and these are all available in the Journal of Applied Mechanics, and they are also available in some reference books. So, it is not necessary to go in for deriving all these relations at this stage. You can make use of these constants and calculate the maximum stress and also maximum deflection. So, this gives you the rigorous calculation for the deflection and stresses in plates of certain geometry. Many times as designer, one would like to do simplified calculations, and if these calculations are to be done, people will try to take simpler approaches just to get some approximate idea, and therefore, I would like to give you some approximate methods of calculation of stresses in the case of circular plates, maybe circular plates with cutouts, and try to understand how these calculations can be done. Let us take a case for approximate calculation of stresses in a circular plate which is simply supported at the edges, subjected to uniformly distributed pressure, and let us say it is of dimension equal to A. If I consider that reaction at the support is uniform, then obviously that reaction R, which is going to come up all over the circumference, can be calculated. And now, if we take a diametral section, then on that section we are going to have bending moment plus shear forces. Now, we are more concerned about the bending moment. On this section we are going to have bending moment coming up, and this bending moment we can assume that they are uniform, they do not have any variation in the radial direction. Although you have seen in the exact calculation there is a variation, but herein we can assume that they are going to remain constant all over the diameter. And now, if we consider that m is the intensity of this moment distribution, rather you can think of it, it is nothing but moment per unit length of this diameter. So, therefore, it is going to be in units Newton meter per meter. The center of gravity of the distributed pressure over that semicircle is going to lie somewhere here. If we consider that this is the other perpendicular direction, then this center of gravity of this pressure is going to lie at a point somewhere at B, and this OB distance, it can be easily calculated, it is going to be nothing but 4a by 3 pi, where a is the radius. Similarly, if you consider that R is the distributed load over the edge of the plate, then this distribution would have a center of gravity at A, which is going to be at a distance of 2a by pi. So, now if we take the moment of all the forces about the diameter, that will help us to calculate the magnitude of this moment. So, we can write the moment equilibrium equation. So, what we have is m into 2a is the total moment in the anti-clockwise direction, and now this load P is also going to give anti-clockwise moment, and that is nothing but P into pi a square by 2, that is the total force acting downward, and its moment term is 4a by 3 pi. So, that is the moment due to the distributed pressure, and now R is going to counteract this moment, and this is going to be now R, and it is acting over a length of pi a semicircle, and its CG is at a distance of 2a by pi. So, therefore, this is the moment equilibrium. So, if we consider now this moment equation, we now have also some of the values here. R is nothing but P into pi a square by 2 pi a, total vertically downward load, and therefore, this is nothing but P a by 2, and once you substitute all this, you find that this m into 2a is nothing but P pi a cube by pi minus 2 times P pi a cube by 3 pi, and on simplification what you find is that this is 1 by 3 P a cube, and therefore, our moment m is nothing but P a square by 6. So, that is the intensity of the moment on the diameter everywhere, and therefore, the maximum stress is going to be given by 6m by h square, and this is nothing but P a square by h square. If you remember, the stress for the simply supported plate of this type, that was nothing but 3 by 8 into 3 plus nu into P a square by h square. So, we had a multiplier here. In the exact formulation, it was 3 by 8 into 3 plus nu. So, this 9 by 8, if you forget nu, 9 by 8, it was approximately 1. Through approximate calculations, we have got that as unity. Now, I will show you the comparison of the exact stress distribution with this approximate value that we have calculated for the whole diameter. So, let us have this plate. This is the center. Now, let us plot the distance in the vertical direction. So, this is my x direction and this is the direction where I would like to plot sigma max. So, if you now consider the exact stress, it is tensile everywhere and the variation is symmetric about the center, and the approximate value that we have obtained is nothing but. So, this is the approximate value that we have got, P a square by h square, and this value is nothing but 3 by 8, 3 plus nu P a square by h square, and this is our exact distribution, and this magnitude here, which is at the outer edge, which is much lower, this is nothing but 3 by 4 into 1 minus nu P a square by h square. So, it is really that approximate calculation can do for a rough estimate, and this is the difference. We will consider some more cases in the next lecture, where we would like to consider plates where the plate is subjected to concentrated loading, and we would also like to look into the case of rectangular plates subjected to uniformly distributed load and simply supported at the edges.